Hey guys, so we're going to be doing some. I'm not sure if the stream has started yet actually, so just give me a minute and I'll check. Okay, it's not showing up right now on my channel, I think. Okay, yeah, it seems to be there now. I'm not sure if the stream has started yet actually. Okay, great. Yeah, it seems to be working now. So let's begin then. And yeah, so let's share the screen. And we're doing so basically we're beginning multivariable calculus on Khan Academy. I've already done um, I've already done like the equivalent of almost done with AP Calculus BC. So this is the logical next step, and we've got time in summer, right? Like it's summer break has just started, so there's enough time to do it as well. So let's begin. I'm not sure how much I'll get done today because I have to go soon and I don't have much time. But let's begin. So actually, I need to charge my computer again. It seems so. I'll be right back. 1 minute. Okay, so I'm back now. Let's go here. Now I'm not going to just be watching the videos here since this is completely new stuff. I'll be taking some notes as well. So let's open that up. I'll take them online here obviously so that you can see it as well. It's easier to organize like this, and then I can after that I can write down paper for myself. So that's perfect. Now let's see. So we're going to begin with. I've already done this, but I'll start. I did this some time ago. I don't really remember all the stuff here, so we'll just start from the beginning. I've skipped the first unit because there's nothing interesting there. You can watch that yourself if you want. And let's go.
But after you make that initial little nudge, so let's say I have some multivariable function like f of xy, so it'll have a two-variable input is equal to, I don't know, x squared times y plus sine. So
One
let's say I
sec.
have some multivariable function like f of xy, so it'll have a two-variable input is equal to, I don't know, x squared times y plus sine of y. So it'll output just a single number, it's a scalar valued function. The question is, how do we take the derivative of an expression like this? And there's a certain method called a partial derivative, which is very similar to ordinary derivatives, and I kind of want to show how they're secretly the same thing. So to do that, let's just remind ourselves of how we interpret the notation for ordinary derivatives. So if you have something like f of x is equal to x squared, and let's say you want to take its derivative, and I'll use the Leibniz notation here, df dx, and let's evaluate it at 2, let's say. I really like this notation because it's suggestive of what's going on. If we sketch out a graph, so I know this x represents our output, this over here represents our input, and x squared has a certain parabolic shape to it, something like that. When we go to the input, x equals 1, 2, this little dx here, I like to interpret as just a little nudge in the x direction, and it's kind of the size of that nudge. And then df is the resulting change in the output after you make that initial little nudge. So
Okay,
this
so
is
there's not
the
really
resulting term
anything
is the
interesting here for now.
for the ratio
Let's
between the two graphs. If you really
skip this
the
part.
same thing, not going to be graphing a function. This is put to the input. How does that influence the output? And in this case, the output, I mean, it's still just a number. So maybe we go off to the side here and we draw just like
Wait, are you being able to hear the audio? Can you like write in the chat if you're being able to hear the video or not?
number line as our output. And somehow we're thinking about the function as mapping points on the plane to the number line. So you say, okay, that's your dx. How much does it change the output? And maybe this time it changes it negatively. It depends on your function. And that would be your df. And you can also do this with the y variable, right? There's no reason that you can't say df dy and evaluate at that same point, 1, 2, and interpret totally the same way. Except this time your dy would be a change in the y direction. So maybe I should really emphasize here that that dx is a change in the x direction here, and that dy is a change in the y direction. And maybe when you change your f according to y, it does something different, right? Maybe, the output increases, and it increases by a lot. It's more sensitive to y. Again, it depends on the function. And I'll show you how you can compute something like this in just a moment here. But first, there's kind of an annoying thing associated with partial derivatives where we don't write them with e's in dx df. People came up with this new notation, mostly just to emphasize to the reader of your equation that it's a multivariable function involved. And what you do is you say, you write a d, but it's got kind of a curl at the top. It's this new symbol, and people will often read it as partial, so you might be like,
Okay, what? Let me Google what that is. Del symbol. Like, what's the actual name of it? Oh, Nabla or something. Okay, the wait. Okay, I don't think that's a. I don't hear what he said. Let me just turn on the subtitles and see.
is you say, you write a d, but it's got kind of a curl at the top. It's this new symbol, and people will often read it as partial, so you might be like partial left, partial y. If you're wondering
Oh,
what
okay,
f of x
partial.
means, it's sort of like this doesn't tell the full story of how f changes because it only cares about the x direction. Neither does this only cares about the y direction. So each one is only a small part of the story. So let's actually evaluate something like this. I'm going to go ahead and clear the board over here. I think the one-dimensional analogy is something we probably have already. So, little remnants. So if you're actually evaluating something like this, here I'll write it again up here. Partial derivative of f with respect to x, and we're doing it at 1, 2. It only cares about movement in the x direction, so it's treating y
So it's like taking the derivative and then you just treat all the other variables. So if you're doing partial f partial x, then you just treat all the variables except x as constants. Right? That's what he's saying, I think.
But instead of writing y, I'm just
I should start writing this down actually. The What is this topic called? Partial derivatives, right? Wait, actually, let's be a bit more organized. This unit is called derivatives of multivariable functions. Here we can open a new like H2. So I'm trying to be as organized as possible. If you guys want, I can like whenever all these notes that I have, I can just link a PDF to them in the chat or something, or in the description or comments. And here what we're doing is we're doing derivatives of multivariable functions, partial derivatives, right? That's where we are. And in here, so the partial derivatives are denoted by the partial sign del, and then how do you write that? Like the partial sign, this thing right here. So I'll copy paste that in. Okay, and then these basically treat all other variables as constant when taking Okay, let's go back.
writing y, I'm just going to plug in that constant ahead of time. Because when you're only moving in the x direction, this is kind of how the multivariable function sees the world. And I'll just keep a little note that we're evaluating this whole thing at x equals 1. And here, this is actually just an ordinary derivative, right? This is an expression that's an x. You're asking how it changes.
Okay, 2x squared, so that'll be 4x. Right, I think that's it.
X squared times 2 is going to be 4x.
4x and then x is 1, so it's just going to be 4, right? Let's check.
When you take the derivative, this is just 1
Yeah.
cosine, so the derivative is 1. This over here, the derivative is cosine. Cosine of y. Again, we're evaluating this whole thing at y equals 2. So your overall answer would be 1 plus cosine of 2. I'm not sure what the value of cosine of 2 is off the top of my head, but that would be your answer. And this is a partial derivative at a point. But a lot of times you're not asked to just compute it at a point. What you want is a general formula that tells you, hey, plug in any point x, y, and it should spit out the answer. So let me just kind of go over how you would do that. It's actually very similar, but this time, instead of plugging in the constant ahead of time, we just have to pretend that it's a constant. So let me make a little bit of space for ourselves here. Really.
Okay, and then, so let's try this ourselves. If you do that, like partial f partial x, that will give you 2xy. Yeah, that's it, just 2xy. Because sine of y will just be treated as a constant. So that should be 2xy. Yeah, and then this one will be x squared plus cosine of y.
You get 1. So I'm sorry, you get 1 plus the cosine of 1, which is what we had before. So this is really what
Yeah, okay, so same, so it's pretty like logical then, exactly what he said. And so yeah, I think we've got all that written over here right now, so that's good.
Input, and you're seeing how that influences things, and then you might move in one direction for another input and see how that influences things. In the next video, I'll show you what this means in terms of graphs and slopes. But it's important to understand that graphs and slopes are not the only way to understand derivatives, because as soon as you start thinking about vector value functions or functions with inputs of higher dimensions than just 2, you can no longer think in terms of graphs. But this idea of nudging the input in some direction, seeing how that influences the output, and then taking the ratio, the ratio of that output nudge to the input nudge, that's a more general way of viewing things, and that's going to be very helpful moving forward in multivariable calc.
Okay, great. Now let's do some practice here. The basic partial derivative. So df dy, you treat y as a constant, so that becomes negative 1 plus x. Sorry, you treat x as a constant there. Here we say x is a constant again, so it's over x, and it'll just become negative sine y over x. Here it'll become, so e to the x is a constant, and so is x squared with respect to this, so that will all be 0. Here if you do it with y, this just becomes 4, because we're leaving the x as a constant and just taking the derivative of 4y with respect to y. This one, what is a partial derivative with respect to y? Natural log of sine of x is just one thing, so it'll just be 2y natural log of sine of x. That's just a constant. It's a partial derivative of h with respect to b. So 2 to the a, we can ignore that. 2 to the a times 1, actually, we can ignore that whole thing. We just get 2 to the a times b, which means 2 to the a. um, the denominator will stay the same. The numerator becomes 2e times 2 to the y, so the 2's cancel out, e to the 2y over x. Here it will become, so it's with respect to x, so this is a constant, minus 2x, it becomes negative cosine x minus 2x. Okay, done. Graphical understanding. I don't think I'll take any notes for this.
Hello everyone. So I have here the graph of a two-variable function, and I'd like to talk about how you can interpret the partial derivative of that function. So specifically, the function that you're looking at is f of xy is equal to x squared times y plus sine of y. And the question is, if I take the partial derivative of this function, so maybe I'm looking at the partial derivative of f with respect to x, and let's say I want to do this at negative 1, 1. So we'll be looking at the partial derivative at a specific point. How do you interpret that on this whole graph?
Let's first evaluate it and see. It's always good practice to do this stuff. So it'll become 2x, right? That's it. And then, yeah, that's it. So 2x, which means it'll be negative 2.
So first, and it's the point that's hidden in the
Sure, we'll watch this.
This is our x-axis, this is our y-axis. The point negative 1, 1 is sitting right there. So negative 1, move up 1, and it's the point that's sitting on the graph. And the first thing you might do is you say, well, when we're taking the partial derivative with respect to x, we're going to pretend that y is a constant. So let's actually just go ahead and evaluate that. So when you're doing this, it says x squared looks like a variable, y looks like a constant, sine of y also looks like a constant. So this is going to be, we differentiate x squared, and that's 2 times x times y, which is like a constant, and then the derivative of a constant there is 0. And we're evaluating this whole thing at x is equal to negative 1, and y is equal to 1. So when we actually plug that in, it'll be 2 times negative 1 multiplied by 1, which is 2. Negative 2, excuse me. So what does that mean, right?
Yeah, so we got that right. Now we need to see the interpretation. Right, so I'm glad there's an actual graph there. We can see what it means. I know some stuff passes like what a gradient is because I watched some of the videos on this, as you can see. But I should take some, once I finish this video, I'll take some notes on this too. Okay, and so far, so let me know in the chat, like if you want. I'm not a great note taker, but I need to like become a good note taker for like to study properly. So if you want, I can like take this, download it as a PDF, all the notes that I'm doing right now, and I can I can just link to that in the description or in the comments or something if you guys want. But while we're doing that, right before that, I'll just watch this video. Now I'm not too sure how much I can do. Let's quickly just like pause for a second and see how much we'll try to do. So obviously unit 1, we're not going past that. We'll do, sorry, unit 2, and we're going to be doing, so we'll do partial derivatives because I think we're almost done with that, at least for the most part. And then we can do gradient and directional derivatives as well. After that, these articles, I don't think those are, there's not really much to do there, I guess. We can read those. I think, yeah, that makes sense. We can stop there at quiz 2. We'll do quiz 2 and then we'll end there. Because after that, then there's some longer stuff. Maybe we can do that a bit later, but not now. And yeah, let's continue then. I'll keep this tab here for now. Let's move on with the video.
This is kind of like nudge in the x direction, this is the resulting nudge of f. What does that mean for the graph? Well, first of all, treating y as a constant is basically like slicing the whole graph with a plane that represents a constant y value. So, this is the y-axis, and the plane that cuts it perpendicularly, that represents a constant y value. This one represents the constant y value 1, but you can imagine it, you can imagine sliding the plane back and forth, and that would represent various different y values. So for the general partial derivative, you can imagine whichever one you want, but this one is y equals 1. And I'll go ahead and slice the actual graph at that point, and draw a red line. And this red line is basically all the points on the graph where y is equal to 1. So I'll just kind of emphasize that, where y is equal to 1, and this is y is equal to 1. So when we're looking at that, we can actually interpret the partial derivative as a slope, because we're looking at the point here, we're asking how the function changes as we move in the x direction. And from single variable calculus, you might be familiar with thinking of that as the slope of a line. And to be a little more concrete about this, I could say, you're starting here, you consider some nudge over there, there's some tiny step, I'm drawing it, as a sizable one, but you imagine it as a really small step as your dx, and then the distance to your function here, the change in the value of your function as your, I said dx, but I should say partial x or del x, partial f. And as that tiny nudge gets smaller and smaller, this change here is going to correspond with what the tangent line does, and that's why you have this rise over run feeling for the slope. And you look at that value, and the line itself looks like it has a slope of about -2, so it should actually make sense that we get -2 over here, given what we're looking at. But let's do this with the partial derivative with respect to y. Let's erase what we've got going on here, and I'll go ahead and move the graph back to what it was, get rid of these guys. So now we're no longer slicing with respect to y, but instead, let's say we slice it with a constant x value. So this here's the x-axis. This plane represents the constant value x equals -1, and we can slice the graph there. We can kind of slice it. I'll draw the red line again that represents the curve. And this time, that curve represents the value x, or equals -1. It's all the points on the graph where x equals -1. And now when we take the partial derivative, we're going to interpret it as a slice, as the slope of this resulting curve. So that slope ends up looking like this. That's our blue line. And let's go ahead and evaluate the partial derivative of f with respect to y. So we'll go over here.
Okay, let's do that ourselves as well. So it'll become plus cosine y, and it'll become x squared. So it'll just become x squared plus cosine of y. Wait, let's take a note here, right? So graphical understanding of partial derivatives. So what do these do? These give slopes of well, like I think lines. These give slopes of tangent lines to curves found after slicing the what's it called, slicing the figure. I think that's, I don't know if this is correct, but it seems right. If I find out otherwise, I'll change it later. But I think that's kind of what he's saying, and I'm assuming that, if there are three variables, he hasn't gone over that yet. But if there are three variables, then I guess you can't just, you'll have to slice it with maybe respect to two different things. I'm not sure. We'll see a bit later. Maybe he'll go over it in this video itself. Not sure.
Use a different color.
But I think what I've written there so far is decent
So
enough.
the partial derivative of f with respect to y, partial y. So we go up here and it says, okay, see x squared times y. It's considering x squared to be a constant.
Yeah, so we got that correct.
But it's something a little bit positive, and the ultimate result that we see here is going to be 1 plus something. I don't know what it is, but it's something positive, and that should make sense because we look at the slope here, and it's a little bit more than 1. I'm not sure exactly, but it's a little bit more than 1. So you often hear about people talking about the partial derivative as being the slope of the slice of a graph, which is great if you're looking at a function that has a 2-variable input and a 1-variable output, so that we can think about its graph. And in other contexts, that might not be the case. Maybe it's something that has a multidimensional output. We'll talk about that later when you have a vector value function, what its partial derivative looks like. But maybe it's also something that has 100 inputs, and you certainly can't visualize the graph. But the general idea of saying, well, if you take a tiny step in a direction, here, I'll actually walk through it in this graph context again. You're looking at your point here, and you say we're going to take a tiny step in the y direction, and I'll call that partial y. And you say that makes some kind of change. It causes a change in the function, which we'll call partial f. And as you imagine this getting really, really small, and the resulting change also getting really small, the rise over run of that is going to give you the slope of the tangent line. So this is just one way of interpreting that ratio, the change in the output that corresponds to a little nudge in the input. But later on, we'll talk about different ways that you can do that. So I think graphs are very useful. When I move that, the text doesn't move. I think graphs are very useful for thinking about these things, but they're not the only way. And I don't want you to get too attached to graphs, even though they can be handy in the context of 2-variable input, 1-variable output. So next video.
Okay, good. That wasn't a very fun video, I think. Let's look here and no, let's not read that actually. Okay, formal definition. I don't think I'll take notes on that since I don't think it'll be like, yeah, this is like limit stuff. I don't want to be writing all that stuff. I want to keep it like notes that are more useful
How you
than
compute it, how you
the
interpret it in terms of
formal
graphs. So what I
definition.
want to do here is give its formal definition. So it's the kind of thing, just to remind you, that applies to a function.
It's more important, I think, to just understand how this works, understand the definition, and just not have to write it.
It has a multivariable input, so x, y, and but I'll just emphasize that it could actually be a number of other inputs. You could have 100 inputs or something like that. And as with a lot of things here, I think it's helpful to take a look at the one-dimensional analogy and think about how we define the derivative, just the ordinary derivative, when you have a function that's just one variable. This would be just something simple, f of x, and maybe you're thinking in the back of your mind that it's a function like f of x equals x squared. And the way to think about the definition of this is to just actually spell out how we interpret this df and dx, and then slowly start to tighten it up into a formalization. So you might be thinking of the graph of this function, maybe it's some kind of curve, and when you think of evaluating it at some point, let's say you're evaluating it at point A. You're imagining dx here as representing a slight nudge, just a slight nudge in the input value. So this is in the x direction. You got your x coordinate, your output f of x is what the y-axis represents here. And then you're thinking of df as being the resulting nudge here, the resulting change to the function. So when we formalize this, we're going to be thinking of a fraction that's going to represent df over dx. And I'll leave myself some room. You can probably anticipate why if you know where this is going. And instead of saying dx, I'll say h. So instead of thinking, dx is that tiny nudge, you'll think h. And I'm not sure why h is used necessarily, but not just having some kind of variable that you think of as getting small, maybe all the other letters in the alphabet were taken. And now when you actually say, what do we mean by the resulting change in f? What we should be writing is, well, where does it go after you nudge? So when you take, from that input point plus that nudge, plus that little h, what's the difference between that and the original function, or the original value of the function at that point? So this top part is really what's representing df. This is what's representing df over here. But you don't do this for any actual value of h. You don't do it for any specific nudge. The whole point, largely the whole point of calculus, is that you're considering the limit as h goes to 0 of this. And this is what makes concrete the idea of tiny little nudge or a tiny little resulting change. It's not that it's any specific one. You're taking the limit, and you can get into the formal definition of a limit, but it gives you room for rigor as soon as you start writing something like this. Now, over in the multivariable world, very similar story. We can pretty much do the same thing, and we're going to look at our original fraction and just start to formalize what we think of each of these variables as representing. That partial x still is common to use the letter h just to represent a tiny nudge in the x direction. And now if we think about what is that nudge, and here let me draw it out actually. The way that I kind of like to draw this out is you think of your entire input space as the xy plane. If it was more variables, this would be a high-dimensional space. And you think of some point, maybe you think of it as a, b. Maybe I should specify that actually. We're doing this at a specific point. How you define it? We're doing this at a very specific point, A, B. And when you're thinking of your tiny little change in x, you'd be thinking, a tiny little nudge in the x direction, tiny little shift there, and the entire function maps that input space, whatever it is, to the real number line. This is your output space. And you're saying, hey, how does that tiny nudge influence the output? I've drawn this diagram a lot. Just this loose sketch. I think it's actually a pretty good model because once we start thinking of higher dimensional outputs or things like that, it's pretty flexible. And you're thinking of this as your partial f, partial x, sorry, your change in the x direction, and this is that resulting change.
Okay, let's slow down the video a bit as well. It's getting a bit. 1.5 seems fine. We'll see.
This function. But we go back up here and we say, well, what does that mean, right? If h represents that tiny change to your x value, well, then you have to evaluate the function at the point A, but plus plus that h, and you're adding it to the x value, that first component, just because this is the partial derivative with respect to x. And the point b just remains unchanged, right? So this is you evaluating it kind of at the new point, and you have to say what's the difference between that and the old evaluation where it was just at a and b.
Okay, good. So this is what I was hoping it would be. Basically the same thing as as this, but you're also taking the input of b, right? So the comma b, that's another input you're taking. So at least this part, like everything so far, seems to make sense. So
And
that's
that's it. That's
good.
the formal definition of your partial derivative. Except, I mean, the most important part, right? The most important
The
part, again,
limit
because
part,
it's calculus, is that we're not doing this for any specific value of h, but we're
limit as h goes
actually,
to 0.
let me just move this guy, give a little bit of room here. Yes. But we're actually taking the limit here, limit as h goes to 0. And what this means is you're not considering any specific size of dx, any specific size of this, really this is h, considering the notation up here, but any size for that partial x. You're imagining that nudge shrinking more and more and more, and the resulting change shrinks more and more, and you're wondering what the ratio between them approaches. So that would be the partial derivative with respect to x. And just for practice, let's actually write out what the partial derivative with respect to y would be. So I'll get rid of some of this one-dimensional analogy stuff here.
Okay, let's try this one ourselves. So just following this, right? So instead of changing the a with the h part, you can just say f of a comma b plus h minus f of a comma b over h, and then you take the limit as h goes to 0. So I'm going to skip ahead and see if that's indeed the case. I think it should be, right? That's what would make sense based on what all he said.
Y value.
Yeah, okay, so that's what we said, and it makes sense.
Value, you're shifting it upwards. So again, this is the partial derivative. The formal definition of the partial derivative looks very similar to the formal definition of the derivative, but I just always think about this as spelling out what we mean by partial y and partial f, and kind of spelling out why it is that Leibniz came up with this notation in the first place. Well, I don't know if Leibniz came up with the partials, but the df dx portion. And this is good to keep in the back of your mind, especially as we introduce new notions, new types of multivariable derivatives, like the directional derivative. I think it helps clarify what's really going on in certain contexts. Great. See you next video.
Okay. I take back what I said. I will actually write like a small amount about this in case it's like ever needed. So formal definition of the partial derivative. So basically, this is a similar definition as the normal derivative, but it takes into account the additional input, and there could be more separate inputs. Okay, that seems good. Now symmetry of the second partial derivative. Symmetry of the second partial derivatives. Okay, let's go. This one seems like it won't be quite as difficult, so I'll put it at 1.75.
So in the last couple of videos, I talked about partial derivatives of multivariable functions. And here, I want to talk about second partial derivatives. So I'm going to write some kind of multivariable function. Let's say it's, I don't know, sine of x times y squared. Sine of x multiplied by y squared. And if you take the partial derivative, you have two options. Given that there's two variables, you can go one way and say, what's the partial derivative of f with respect to x? And what you do for that, x looks like a variable as far as this direction is concerned, y looks like a constant. So you differentiate this by saying the derivative of sine of
So this would be y squared cosine of x.
is cosine x.
Following that would be, yeah, partial f partial x.
That'll be that constant.
And then this one will be sine of x remains a constant. So it'll be 2y sine of x, or 2 sine of x times y.
Sine of x. And over here, similarly,
Yeah, okay, same thing, correct.
you'd say f with a little subscript x. Now, each of these two functions, these two partial derivatives that you get, are also multivariable functions. They take in two variables and they output a scalar. So we can do something very similar, where here you might then apply the partial derivative with respect to x.
Okay, and then this here would give us negative sine y squared.
To that partial derivative of your respect to x. Right here, it just looks like a constant, so it just stays constant at y squared. Function, which itself is a partial derivative with respect to x.
Okay, wait, I think there is something like very interesting here. I think if you take the partial of x, so if you do, I don't know, I forgot like how you say it correctly, but I think there's going to be a symmetry where this part, wait, I think you can see my mouse, I'm not sure. But basically, the partial y of partial f partial x will be partial x of partial f partial y, right? I think basically, well, let's just see if it's correct or not. Okay, first of all, this will be what, 2y cosine x, right? 2y cosine x.
Partial squared of f. They always threw me off because
Okay, and that syntax there is, I think that's the same as like for actual function, right? It's like dy d squared, yeah. So that dy dx, and then you put the square in front of the D and then at the bottom there. So this syntax is also the same.
Because it's as if I go down the path of x cosine x. Pretty cool thing worth pointing out here.
Okay, yeah, that's what I was thinking as well. But I remember like somewhere that and obviously symmetry, symmetry of second partial derivatives. That implies that there's some symmetry, and I guess that's what they're talking about then. Let's finish it off. The second like second partial derivative of f with respect to y will be the derivative of this with respect to y, which means it'll be 2 sine x.
You first take the part, you'd say x that the original function just is actually a.
Oh wait, he's not
You
going
do it the other way around, when instead
over
of
that,
x
I
and
think.
y, you do y and then x, partial x. That these guys are equal to each other. And that's a pretty.
Okay, so you're doing. So what is he saying? He's saying basically that. So basically you're doing partial. I think he's trying to just show that these two are equal because in the denominator you'll have partial x, partial y. I don't think that's how it actually works. I don't think you can multiply it. He said that before, but it's an intuitive approach. Like these two look equal, and I think basically what he's saying is that it's not rigorously, like that's not the rigorous way to go about proving it, but that is the intuitive way to say it, that like you'll have the same things here. It's just that you multiply them in a different order, so it's commutative or associative. I'm not sure.
Pretty cool.
But sorry about that. I think that unless I think he's going to show it, but basically the second partial derivative with respect to y should be 2 sine x. I think just for some extra practice.
Given that the original function just looks like the product of two things, you can kind of reason through why it's the case. But what's surprising is that this turns out to be true for, I mean, not all functions. There's actually a certain criterion. There's a special theorem. It's called Schwarz's theorem. Not all functions. There's actually a certain criterion. There's a special theorem. It's called Schwarz's theorem.
Okay, let's write that down and let's actually create a new header for this. I forgot to do that. So heading 3, what is this? Symmetry of second partial derivatives. Or let's just write second partial derivatives. That's more general. So this is done in the same way as traditional derivatives. And then what else is there? So yeah, partial. Wait, I don't think you can do like latex or whatever here. So let's just do. Yeah, I think this is it then, right? I want to make sure I've written it correctly. So that seems right. Yeah, this is the rule. No, wait. Back, enter. Okay, here. This is done the same way as traditional derivatives. This holds for. Okay, this is Schwarz's theorem, right? What is it called? Let's check the subtitles here.
Where if the second partial derivative a certain criterion, there's a special theorem. It's called Schwarz.
So, German name, I'm guessing. Schwarz's theorem. So, see, okay, whatever. Schwarz. This is Schwarz's theorem. Doesn't hold for all functions. All functions. Let's Google when this does hold. And if we can understand it, then we like it. If we can't, then we just let it be. So, Schwarz's theorem, multivariable calculus. Oh, there's no E. Okay. I misspelled theorem as well. Let's look. So, okay, when does this happen? What is symmetry of the second derivatives? Let's quickly read it. If we don't understand it, obviously leave it. But if in case we understand anything, that's good. Okay, yeah, this is getting a bit too complex, I think. Well, is the assertion that second. Okay, this is like too complicated as I was expecting. So we'll just let it be. Doesn't hold for all functions. I think that's enough to know for now.
Schwarz's theorem. where if the second partial derivatives of your function are continuous at the relevant point, that's the circumstance with
Oh,
the
he's
Schwartz's
saying it.
theorem, where if the second partial derivatives of your function are continuous at the relevant point,
If the second partial derivatives are continuous, doesn't hold for all functions. Second derivatives, partial derivatives of the function must be continuous.
that's Schwartz's theorem, where if the second partial derivatives of your function are continuous at the relevant point,
Are continuous, must be continuous at the point in question. Because I'm guessing you usually do this when you're given a point. Must be continuous at the point in question. Okay, good. We've got
that's
that
considered
done.
as being true. But for all intents and purposes, the kind of functions you can expect to run into, this is the case. This order of partial derivatives doesn't matter truth turns out to hold, which is actually pretty cool. And I'd encourage you to play around with some other functions. Just come up with any multivariable function, maybe a little bit more complicated than just multiplying two separate things there, and see that it's true, and maybe try to convince yourself why it's true in certain cases. I think that would actually be a really good exercise. And just before I go, one thing I should probably mention, a bit of notation that people commonly use. With the second partial derivative, sometimes instead of saying partial squared f partial x squared, they'll just write it as partial and then xx. And over here, this would be partial, let's see, first you did it with x, then y, so over here you do it first x and then y, kind of the order of these reverses, because you're reading left to right, but when you do it with this, you're kind of reading right to left for how you multiplied in. Which would mean that this guy, let's see, this guy over here, he would be partial first you did the y, and then you did the x. So those two guys are just different notations for the same thing. And that can
Okay, so this is also denoted like that. I don't know how to write that stuff here. Let's see. Yeah, I don't know how to do that. So let it be. I'll just have to keep that in my mind and remember. Okay, yeah.
make it a little bit more convenient when you don't want to write out the entire partial squared f divided by partial x squared or things like that. And with that, I'll call it an end.
Okay, now let's do some practice here. I've got my writing thing here actually. So that's, yeah, and this is already a third derivative. So that's fine. Well, let's see. Third derivative. So third partial derivative, I guess. We're doing it with respect to x, right? So y to the fourth is just a constant. And then you're multiplying it by, so 6x. So 6xy to the fourth. Wait. So the first derivative, oh, sorry, just 6. Yeah, I forgot it. I actually took the second derivative, which is obviously wrong. I got saved there by the error, by the syntax thing. So that's good. Now let's see. Second derivative with respect to y this time. So x, y. Let's actually just break it up. Do this in our heads actually. That's probably the best. So x, y, when you take the derivative, it'll just become x. When you take the derivative, it's a constant. So that becomes 0. You have now negative sine of y. So you take the derivative of negative sine of y times x, which will give you negative cosine of y. Take the derivative of that, you get sine of y. So you get x sine y. Okay, this is basically you take the partial with respect to x, then with y, partial x, partial y, right? And so if you do it with y first, I think that might be easier. You'll get 4x plus e to the y. And then if you do it with x, the e to the y goes away. You get 4x, which means it's just 4. Okay, good. Uh, and wait, I don't remember exactly what I did there. I might have started with the wrong letter. Like it says d partial x partial y. I might have done partial y then partial x. That comes from what we just learned, the Schwarz's theorem. Okay, so I just did it from there. Here we're taking it with respect to x. So this should actually just be 0 because e to the y is a constant. You're taking the derivative of x twice, which is 0. Okay, done. Good. So not bad at all actually. We're already done with the first one. Now gradient and directional derivatives. Okay, so let's go with gradient. I don't know what a contour map is, so maybe we'll just stop there then. Let's watch this.
So here I'm going to talk about the gradient. And in this video,
Okay, this is a bit fast, so let's slow it down to 1.5 and see.
I'm only going to describe how you compute the gradient, and in the next couple ones, I'm going to give the geometric interpretation. And I hate doing this. I hate showing the computation before the geometric intuition, since usually it should go the other way around. But the gradient is one of those weird things where the way that you compute it actually seems kind of unrelated to the intuition. And you'll see that. We'll connect them in the next few videos, but to do that, we need to know what both of them actually are. So, on the computation side of things, let's say you have some sort of function, and I'm just going to make it a two-variable function, and let's say it's f of xy equals x squared sine of y. The gradient is a way of packing together all the partial derivative information of a function. So let's just start by computing the partial derivatives of this guy. So partial of f with respect to x is equal to, so we look at this and we consider x the variable and y the constant. Well, in that case, sine of y is also a constant. As far as x is concerned, the derivative of x is 2x. So we see that this will be 2x times that constant sine of y. Sine of y. Whereas the partial derivative with respect to y, now we look up here and we say x is considered a constant, so x squared is also considered a constant. So this is just a constant times sine of y. So that's going to equal that same constant times the cosine of y, which is the derivative of sine. So now what the gradient does is it just puts both of these together in a vector. And specifically, and I'll change colors here, you denote it with a little upside-down triangle. The name of that symbol is nabla, but you often just pronounce it del. You'd say del f or gradient of f.
Okay, let's pause. This is denoted with nabla del nabla del. This packs together in a vector. Okay, so denoted with nabla or del, which is the upside down triangle. I'll just like, oh wait, let's just get the copy paste the symbol then. Okay, good. Let's continue then.
And what this equals
Okay, and let's see let's see the definition here.
is a vector that has those two partial derivatives in it. So the first one is the partial derivative with respect to x, 2x times sine of y. And the bottom one, partial derivative with respect to y, x squared cosine of y. And notice, maybe I should emphasize, this is actually a vector valued function, right? So maybe I'll give it a little bit more room here and emphasize that it's got an x and a y. This is a function that takes in a point in two-dimensional space and outputs a two-dimensional vector. So you could also imagine doing this with three different variables.
Okay, let's write like a general formula then for this. Right, so let's say you've got x, y, and so on. Then here you'll write the partial, which is this. So so df dx, and then you'll do df dy, and so on. So I think that seems to be right. Right, this is the gradient, and that's the way you store it in a vector. So that's how it's done.
Then you would have three partial derivatives and a three-dimensional output. And the way you might write this more generally is we could go down here and say the gradient of any function is equal to a vector with its partial derivatives. Partial of f with respect to x, and partial of f with respect to y. And in some sense, we call these partial derivatives, I like to think of the gradient as the full derivative because it kind of captures all of the information that you need. So a very helpful mnemonic device with a gradient is to think about this triangle, this nabla symbol, as being a vector full of partial derivative operators. And by operator, I just mean, here let's like partial with respect to x, something where you could give it a function and it gives you another function. So you give this guy, the function f, and it gives you this expression, this multivariable function as a result. So the nabla symbol is this vector full of different partial derivative operators, and in this case it might just be two of them. And this is kind of a weird thing, right? Because it's like, this is a vector, it's got like operators in it, that's not what I thought vectors do, but you can kind of see where it's going. It's really just you could think of it as a memory trick, but it's in some sense a little bit deeper than that. And really when you take this triangle and you say, okay, let's take this triangle, and you can kind of imagine multiplying it by f, really it's like an operator taking in this function and it's going to give you another function. It's like you take this triangle and you put an f in front of it, and you can imagine like this part gets multiplied, quote unquote, multiplied with f, this part gets quote unquote multiplied with f, but really you're just saying you take the partial derivative with respect to x and then with y, and on and on. And the reason for doing this symbol comes up a lot in other contexts. There are two other operators that you're going to learn about called the divergence and the curl. We'll get to those later, all in due time. But it's useful to think about this vector-ish thing of partial derivatives. And I mean, one weird thing about it, you could say, okay, so this nabla symbol is a vector of partial derivative operators. What's its dimension? And it's like how many dimensions do you got? Because if you
the number of dimensions should be like the number of inputs in f, right?
had a three-dimensional function, that would mean that you should treat this like it's
Number of dimensions of f.
got three different operators as part of it. And I'd kind of finish this off down here. And if you had something that was 100-dimensional, it would have 100 different operators in it. And that's fine. It's really just, again, kind of a memory trick. So with that, that's how you compute the gradient. Not too much to it. It's pretty much just partial derivatives, but you smack them into a vector. Where it gets fun and where it gets interesting is with the geometric interpretation. I'll get to that in the next couple of videos. It's also a super important tool for something called the directional derivative. So you've got a lot of fun stuff ahead.
Okay, we've taken the notes for that already. Let's quickly do this. I might not do all of them. Actually, I will. This will take. This will just be the sum of the other two variables, right? Wait, actually, this one. So it should be 4. Then this one will be -3. And this one will be -1. I'm not going to lock that in yet, but so based on the pattern there, if you like take the derivative with respect to x, the x's will get cancelled, you get y plus z. So for any of them, you'll just get the sum of the other two. So this seems right. Okay, good. So you have to take the derivative with respect to just x plus a constant. Um, Kind of forgot how to do this actually. So let's see, how do you do this? Well, like let's say you're doing df dx, right? What is this going to be? It'll be the same for y, right? Because it's symmetric, x squared and plus y squared. So this will be, wait, what are you doing here? It's like x squared plus y squared. You're taking the derivative of this, right? Why am I like blanking on this? Uh, and so it's basically going to be, but why is this so hard? Like, it's just another constant. It doesn't matter, right? Okay, figure it out. X squared plus y squared is, you have to use a chain rule here, I guess, right? So when you take the derivative of this now, you'll get 2x divided by, I think I'm doing this wrong actually. So you're dividing it by this, right? Which means you'll take this to the -2 power. No, wait, what am I saying? Now you've got this here, and this is to the -1. So you do negative x squared plus y squared to the -2. So that means you put a negative in front, you put x squared plus y squared squared. Okay. -2x over this. Similarly, then the other one will be, wait, x squared. Wait, I think this is wrong. This one will just be the same thing, but now with a -2y on top. Okay, correct. Thank God. This one, so with the x, that the this just becomes zy minus 1. With y, this becomes plus 1 over y. So x z plus 1 over y. And for z, this will just become xy. Okay, good. Now when we do this with the x, oh wait, this is easy. So 2y means you'll get, well, just 2y, which is 6, with the other one, with the partial x, 1 over x, so 1. That's it. Okay, good, good, good. Gradients and graphs. I want to keep all this under the one, just the gradients thing here. Just to like save some space. So let's move on to the graphical interpretation, or whatever, gradients and graphs.
So here I'd like to talk about what the gradient means in the context of the graph of a function. So in the last video, I defined the gradient, but let me just take a function here and the one that I have graphed is x squared plus y squared. F of xy equals x squared plus y squared. So two-dimensional input, which we think about as being kind of the xy plane, and then a one-dimensional output that's just the height of the graph above that plane. And I defined in the last video the gradient to be a certain operator. An operator just means you take in a function and you output another function. And we use this upside-down triangle. So it gives you another function that's also of x and y, but this time it has a vector-valued output. And the two components of its output are the partial derivatives. Partial of f
It'll be 2x and
is
2y.
vector x, and the derivative is 0. So this ultimate function that we get the gradient, which takes in a two-variable input, x, y, some point on this plane, but outputs a vector, can nicely be visualized with a vector field. And I have another video on vector fields if you're feeling unsure, but I want you to just take a moment, pause if you need to, and guess, or try to think about what vector field this will look like. I'm going to show you in a moment, but what's it going to look like? The one that takes in x, y, and outputs 2x, 2y. All right, have you done it? Have you thought about what it's going to look like? Here's what we get. It's a bunch of vectors pointing away from the origin. And the basic reason for that is that if you have any given input point, and say it's got coordinates x, y, then the vector that input point represents would, if it went from the origin here, that's what that vector looks like, but the output is 2 times that vector. So when we attach that output to the original point, you get something that's 2 times that original vector, but pointing in the same direction, which is away from the origin. I kind of drew it poorly here. And of course, when we draw vector fields, we don't usually draw them to scale. You scale them down, just so that things don't look as cluttered. That's why everything here, they all look the same length, but color indicates length. So you should think of these red guys as being really long, the blue ones as being really short. So what does this have to
Okay, I didn't actually know that stuff. I think I get it, but okay, so vector fields are something to know about then, obviously.
do with the graph of the function? There's actually a really cool interpretation. So imagine that you are just walking along this graph. You're a hiker and this is a mountain, and you picture yourself at any old point on this graph. Let's say, what color should I use? Let's say you're sitting at a point like this, and you say, what direction should I walk to increase my altitude the fastest?
Okay, yeah, this part I think I know. So the gradient will tell you the vector that you have. It'll tell you which part, like which direction to go, so that you ascend at the fastest rate, right?
want
Like,
to get uphill as
what's
quickly
the
as possible.
fastest way to
At
get
this
up?
point, you might walk, what looks like straight up there. You certainly wouldn't go around in this way. You wouldn't go down. So you might go straight up there. And if you project your point down onto the input space, so this is the point above which you are, that vector, the one that's going to get you going uphill the fastest, the direction you should walk, for this graph, it should kind of make sense, is directly away from the origin. Because here, I'll erase this because once I start moving things, that won't stick. If you were to look at things from the very bottom, any point that you are on the mountain, on the graph here, and when you want to increase the fastest, you should just go directly away from the origin, because that's when it's the steepest. And all of these vectors are also pointing directly away from the origin. So people will say the gradient points in the direction of steepest ascent.
So that's the thing to write down then. The gradient points in the to the direction of steepest ascent. Okay, I will actually put these notes in the description as a PDF file, because I think by the time I'm done, there will be like this could be useful to you guys as well. Let me know, because see, I have like it's not, I know some of the stuff already. I think I've been pretty thorough so far with general information. So if you guys want, I can definitely put that. Let me know in the chat if you want that. Actually, just like write yes, no, or put a thumbs up if you want me to put it there. Otherwise I don't think I will. It's like some no need to do that work if no one needs it. But if you want it, yeah, definitely write it. I can download it and put it in.
Might even be worth writing down. Direction of steepest ascent.
Yeah, he's even telling us to write it up. So.
And let's just see what that looks like in the context of another example. So I'll pull up another graph here. Pull up another graph and its vector field. So this graph, it's all negative values. It's all below the xy plane, and it's got these two different peaks. And I've also drawn the gradient field, which is the word for the vector field representing the gradient, on top. And you'll notice near the peak, all of the vectors are pointing kind of in the uphill direction, sort of telling you to go towards that peak in some way. And as you get a feel around, you can see here this very top one, like the point that it's stemming from, corresponds with something just a little bit shy of the peak there. And everybody's telling you to go uphill. Each vector is telling you which way to walk to increase the altitude on the graph the fastest. It's the direction of steepest descent. And that's what the direction means, but what does the length mean? Well, if you take a look at these red vectors here. So red means that they should be considered very, very long. And the graph itself, the point they correspond to on the graph is just way off screen for us, because this graph gets really steep and really negative very fast. So the points these correspond to have really, really steep slopes, whereas these blue ones over here, it's kind of a relatively shallow slope. By the time you get into the peak, things start leveling off. So the length of the gradient vector actually tells you the steepness of that direction of steepest descent. But one thing I want to point out here, it doesn't really make sense immediately looking at it why just throwing the partial derivatives into a vector is going to give you this direction of steepest descent. Ultimately, it will. We're going to talk through that, and I hope to make that connection pretty clear. But unless you're some kind of intuitive genius, I don't think that connection is at all obvious at first. But you will see it in due time. It's going to require something called the directional derivative. See you next video.
Okay, now, so I know about this part. Okay, let's do this exercise. I was doing this a few days ago as well. Let's try it. So what's the gradient drawn like this? So this is again the steepest ascent, right? So you have to go up, which means it'll be in like this direction. This direction. Wait. Okay, so it's the fastest ascent. And I think that there are 2 points for that, right? You can go either up to the left or to the right. There are 2 points then. Maybe it's B then, or I don't think it'll be zero. It's probably B. Or okay, then it must be zero. Since there's, let's see why it's when it's zero though. He hasn't really said that. Okay, so when is it flat like a plateau? So the gradient is only zero if going in any direction keeps a value of f roughly constant. For 2D scalar fields, this corresponds to where the graph of f is flat like a plateau. The gradient is zero because p is at the maximum and the minimum of two different parabola-like curves aligned diagonally. Um, okay, so I think here anywhere you went, there like there's more than one direction that would take you up. So there's no one clear answer. So they just say the the gradient is zero. Or actually, we can also think about it as well. I don't know. Okay, let's try it again and let's see. A lot of these questions are pretty obvious. Like here, it'll be in that direction. In Sorry, to the right. You have to go up this part, right? That's the steepest ascent. The negative gradient, you just like put it opposite basically. So here it'll be going that way. So this will be going this way. Um, Here to go up, you have to go. Well, again, I think here there are multiple bays, right? Like you can go straight up. You can go towards the z-axis, like right towards the z-axis, or you can go left, like directly leftwards. So I'm going to say it's zero. Okay, no. Then I'm guessing it's C. That's the upward direction. Let's see why it is though. Okay. Gradient codes the direction to travel. Yeah, this is the steepest ascent. Okay, wait, I think I get it now. I had some issues with it, but I get it now. Negative gradient, so instead of going this way, it'll be like this way. That's probably the steepest descent then. Or wait, not necessarily, I think. I'm not sure. Okay, let's do it again. Let's make sure we get it correct this time. This one's a plateau one. We know it's zero. We just had this question. What is a negative gradient? That will be going like in this direction towards the axes, like this one here. What is a gradient for this? Well, it'll be like going straight up towards that edge there, which would be this. Okay, come on, let's get the last one right. Okay, this is a plateau again, right? Anywhere you go, like it should be the same anywhere you go. So the gradient has to be zero. Okay, finally we got that right. We should write that. That's worth writing. The gradient is zero when um the point is on a plateau. When the point on a graph obviously is on a plateau. Okay, so that seems good. Gradient and contour maps. I don't know what contour maps are, to be honest, so that's not good, but let's try it anyway. Let's see.
With something context of a, so here I want to talk about the gradient in the context of a contour map. So let's say we have a multivariable function, a two-variable function, f of x, y, and this one is just going to equal x times y. So we can visualize this with the contour map just on the xy plane. So what I'm going to do is I'm going to go over here, I'm going to draw my y-axis and my x-axis. Right, so This right here represents x values, this represents y values, and this is entirely the input space. And I have a video on contour maps if you are unfamiliar with them or are feeling uncomfortable. And the contour map for x times y looks something like this. And each one of these lines represents a constant value. So you might be thinking that you have, let's say you want to, the constant value for f of x times y is equal to 2 would be one of these lines. That would be what one of these lines represents. And a way you can think about that for this specific function is you're saying, hey, when is x times y equal to 2? And that's kind of like the graph y equals 2 over x. And that's where you would see something like this. So all of these lines, they're representing constant values for the function. And now I want to take a look at the gradient field. And the gradient, if you'll remember, is just a vector full of the partial derivatives of f. And let's just actually write it out. The gradient of f, with our little del symbol, is a function of x and y. And it's a vector valued function whose first coordinate is the partial derivative of f with respect to x. And the second component is the partial derivative with respect to y. So when we actually do this for our function, we take the partial derivative with respect to x, it takes a look, x looks like a variable, y looks like a constant, the derivative of this whole thing is just equal to that constant, y, and then kind of the reverse for when you take the partial derivative with respect to y. Y looks like a variable, x looks like a constant, and the derivative is just that constant, x. And this can be visualized as a vector field in the xy plane as well, at every given point, xy, so you kind of go like x equals 2, y equals 1, let's say, so that would be x equals 2, y equals 1. You would plug in the vector and see what should be output. And
Okay, wait, so this is somewhere. I'm not going to take notes on this, at least not too many, but we should still definitely look at it in detail. So he's taken the gradient here and he's got that there. And let's see what are the contour map is.
kind of swaps though. So we're looking somehow to draw the vector 1, 2. So you would expect to see the vector that has an x component of 1 and a y component of 2. Something like that. But it's probably going to be scaled down.
So basically it's like you're putting the directional derivative, you're putting the, I don't know why I said that. We haven't learned that yet. I don't know what that is. But you're putting the gradient, you're putting the vector at each point. So you're passing in a value to f, and then you're spitting out um, the gradient, right?
Because of the way we usually draw vector fields, and the entire field.
And then I think the color thing is that you basically scale them all to the same length, and then the cool colors like blue and stuff, those are smaller. I think blue is the smallest, and then red is the longest. So that gives you the length. You don't actually draw out the lengths.
Looks like this. So I'll go ahead and erase what I had going on, since this is a little bit clearer. And remember, we scale down all the vectors. The color represents length, so red here is super long, blue is going to be kind of short. And one thing worth noticing, if you take a look at all of the given points around, if the vector is crossing a contour line, it's perpendicular to that contour line.
Okay, so vectors are always. Let's kind of describe this in more detail though. So let's go here. On a contour map, when you graph out, when you like draw out the, when you draw out the what? When you draw out the gradient. And now the first thing is that whenever the gradient passes a contour line, it is a contour line or contour curve.
Wherever you look at all, color represents length. So red here is super long, blue is going to be kind of short.
Oh wait, red is long and blue is short, but it's the other way. Okay, then I might have said it the wrong way. Apparently blue is longer, which makes sense. Yeah, okay. Red is small, so I was wrong about that. Sorry.
Look at all of the given points around. If the vector is crossing a contour line, it's perpendicular to that contour line. Wherever you go, you go down here, this vector is perpendicular to the contour line. Over here, perpendicular to the contour line. And this happens everywhere, and it's for a very good reason. And it's also super useful. So let's just think about what that reason should be. Let's zoom in.
Okay, I wrote down what he said just now. And now we need to figure out the reason and mention that as well, obviously, for the
We're going to
notes.
clear up our function here, clear up all of the information about it, and just zoom in on one of those points. So let's say like right here. We'll take that guy, kind of imagine zooming in and saying what's going on in that region. So you've got some kind of contour line, and it's swooping down like this. And that represents some kind of value. Let's say that represents the value f equals 2. And, it might not be a perfect straight line, but the more you zoom in, the more it looks like a straight line. And when you want to interpret the gradient vector, if you remember in the video about how to interpret the gradient in the context of a graph, I said it points in the direction of steepest descent. So if you imagine all the possible vectors kind of pointing away from this point, the question is, which direction should you move to increase the value of f the fastest? And there's two ways of thinking about that. One is to look at all of these different directions and say which one increases x the most. But another way of doing it would be to get rid of them all and just take a look at another contour line that represents a slight increase. Right? So let's say you're taking a look at a contour line, another contour line, something like this, and maybe that represents something that's right next to it, like 2.1. That represents, another value that's very close. And if I were a better artist and this was more representative, it would look like a line that's parallel to the original one. Because if you change the output by just a little bit, the set of endpoints that look like it is pretty much the same, but just shifted over a bit. So another way we can think about the gradient here is to say of all of the vectors that move from this output of 2 up to the value of 2.1, you're looking at all of the possible different vectors that do that, which one does it the fastest? And this time, instead of thinking the fastest as constant length vectors, what increases it the most, we'll be thinking constant increase in the output, which one does it with the shortest distance? And if you think of them as being roughly parallel lines, it shouldn't be hard to convince yourself that the shortest distance isn't going to be, any of those. It's going to
Okay, yeah. So like between two lines, the shortest distance is a perpendicular line between them. I think that's what he's saying there. So it's wait, I don't even know what contour maps are, to be honest. Let me just contour maps. Contour maps calculus. One-dimensional output, for example. Okay, so I think that this will be obviously useful to know for solving this stuff. Our way to depict functions with two-dimensional input and a one-dimensional output. For example, consider this: x y comma f x y. Okay, yeah. So this format is what we were seeing with that x squared plus y squared, like that shape type of thing. That's a traditional way, but it's obviously clunky or difficult to do. It's hard to show like when you're drawing it. So you start with a graph. So the xy plane, you slice it parallel to that. Oh wait, I did xy plane wrong. Oh, sorry, xy is like this. So it's like horizontal for me right now, like perpendicular to me. I'm like the z-axis. So okay, you're doing it like that. You're slicing it perpendicular to the z-axis, and label the heights that they correspond to. Okay, what are you doing? So you're cutting it out. You're cutting out those. You're cutting out the. You're doing cross sections, and the shapes that you get from those cross sections, you're projecting them, and you're labeling the heights that they correspond to. So you're just projecting it there, and then you're labeling the heights. How are they labeling the heights here? The heights that they correspond to, meaning the z values at which you did that. So you just push it all onto a map, and now you're doing this to -2. So that's at -2, -1. Okay, I think I kind of get it. Let's keep going and seeing. Paraboloid. Okay, let's actually try to see how this would work then. So if you keep on cutting it like that, cross sections, you just have like a lot of um like circles on top of each other. So it'll just be a circular thing, right? Okay, great. We got that correct. And then the levels, like the 1, 2, 3, 4, 5, they just refer to how, like at what x value you sliced it. Sorry, at what z value you sliced it. Okay, that makes sense. Okay, this is like a way to visualize it then, right? And over here, he's not really drawing it, but I guess that's what they're saying then, right? They're saying that, wait, actually, let it be. Let's continue with the article here and see. Waves. So, okay, now if you go to the wave, it would be like, so you'd be cutting it and it would be, oh, okay. I don't know what it would look like. That looks pretty 0, 1, 0, 4, and then, okay, so that's a bit complicated. Its graph is a slanted plane. Okay, this one should like make a lot of sense then if you're doing it. With respect to the z-axis, it'll just be a line and another line and stuff, right? It'll just be like lots of lines. Okay, good. And a literal map. Oh, okay. Contour maps are often used in actual maps to show altitude in hilly terrains. Okay, good. So contour maps can be used for a lot of other stuff. Good. Wait. So this is useful. I should have known that before. But oh, wait. I'm actually stupid. All of this is in Unit 1. You're supposed to know all this stuff in the first place. Vector fields, contour. contour maps. I don't even know if I'm saying the word correctly right now, so it's not a good thing. Maybe I should have done unit one first then actually. And it's not even that hard. I think it's like what this is like 13 units. That's only 6 units, so it's not that long. And I should know a lot of this stuff already, like transform, like vectors and matrices, right? That's not really complicated stuff. Let's continue with this thing quickly, finish it off, and then okay. Now this is getting a bit more into like geography stuff, right? Isobars and isotherms. I don't want to do that. Let's skip it. Okay, I think that's good. And yeah, like the smaller and the smaller things, that means you're going to a peak, which obviously makes which makes sense as well because it's like getting closer and closer to that point right there. Like as for an inverted peak of the graph. Yeah, okay, that also makes sense. Like if it's a valley going like this and then enclosing, it's like you have a mound with a cone in it, and then you just yank the cone out, right? That'll leave a point at the bottom there. Okay, so this stuff is making sense. That's the and steepness is by how close they are. Okay, that definitely helps out quite a bit. That helps out a bit, but actually quite a bit. Okay, I think I got it now. Let's see. So if a vector is crossing a contour line, it is perpendicular. Okay, let's leave it at that then. I'm not going to write out too much stuff there. This seems good. And we finished the video, right? Or no, we didn't. We've got some more.
I'm
Let's just continue now. Let's finish this video off and then do the other videos. I don't have much longer to do this stuff actually. I've already been doing this stream for about an hour, so that's pretty
something
long.
that's pretty much perpendicular to the original line. Because if you think about these as lines, and the more you zoom in, the more they pretty much look like parallel lines, the path that connects one to the other is going to be perpendicular to both of them. So because of this interpretation of the gradient as the direction of steepest descent, it's a natural consequence that every time it's on a contour line, wherever you're looking, it's actually perpendicular to that line. Because you can think about it as getting to the next contour line as fast as it can, increasing the function as fast as it can. And this is actually a very useful interpretation of the gradient in different contexts. So it's a good one to keep in the back of your mind. Gradient is always perpendicular to contour lines. Great. See you next video.
Okay, gradient is always perpendicular to contour lines. Directional derivative. Let's do that. That's the last one. No, not the last one. We might actually just stop like you know. Okay, we will finish this thing. We'll finish this entire unit.
V, at least if you're thinking of V as stemming from the. Hello everyone. So here I'm going to talk about the directional derivative, and that's a way to extend the idea of a partial derivative. And partial derivatives, if you'll remember, have to do with functions with some kind of multivariable input, and I'll just use two inputs because that's the easiest to think about. And it could be some single variable output. It could also deal with vector variable outputs. We haven't gotten to that yet. So we'll just think about a single variable, ordinary real number output that's, an expression of x and y. And the partial derivative, one of the ways that I said you could think about it is to take a look at the input space, your x and y plane. So this would be the x-axis, this is y. And, vaguely in your mind, you're thinking that somehow this outputs to a line. This outputs to just the real numbers. And maybe you're thinking about a transformation that takes it there, or maybe you're just thinking, okay, this is the input space, that's the output. And when you take the partial derivative at some kind of point, so I'll write it out like partial derivative of f with respect to x at a point like 1, 2, you think about that point, 1, y is equal to 2, and if you're taking with respect to x, you think about just nudging it a little bit in that x direction, and you see what the resulting nudge is in the output space, and the ratio between the size of that resulting nudge and the original one, the ratio between, partial f.
Okay, let's slow it down a bit. It's getting a bit fast here. I'll just put it at normal for now.
And partial y is equal to 2, and if you're taking it with respect to x, you think about just nudging it a little bit in that x direction, and you see what the resulting nudge is in the output space. And the ratio between the size of that resulting nudge and the original one, the ratio between, partial f and partial x, is the value that you want. And when you did it with respect to y, you were thinking about traveling in a different direction. Maybe you nudge it straight up, and you're wondering, okay, how does that influence the output? And the question here, with directional derivatives, what if you have some vector, v, and I'll give a little vector hat on top of it, that, I don't know, let's say it's -1
Hi, Yash Dalai.
is the vector. So you'd be thinking about that as a step of -1 in the x direction, and then 2 more in the y direction. So it's going to be something that ends up there. This is your vector v, at least if you're thinking of v as stemming from the original point. and you're wondering what does a nudge in that direction do to the function itself. And remember, with these original, nudges in the x direction, nudges in the y, you're not really thinking of it as, this is kind of a large step. You're really thinking of it as something itty bitty bitty. It's not that, but it's really something very, very small. And formally, you'd be thinking about the limit. As this gets really, really, really small, approaching 0, and this gets really, really small, approaching 0, what does the ratio of the two approach? And similarly with the y, you're not thinking of it as something, this is pretty sizable, but it would be something really, really small. And the directional derivative is similar. You're not thinking of the actual vector actually taking a step along that, but you'd be thinking of taking a step along, say, h multiplied by that vector. And h might represent some really, really small numbers. So, maybe this here is like 0.001. And when you're doing this formally, you'd just be thinking the limit as h goes to 0. So the directional derivative is saying when you take a slight nudge in the direction of that vector, what is the resulting change to the output? And one way to think about this is you say, well, that slight nudge of the vector, if we actually expand things out, and we look at the definition itself, it'll be negative h, negative 1 times that component, and then 2h here. So it's kind of like you took negative 1 nudge in the x direction, and then 2 nudges in the y direction. So for whatever your nudge in the v direction there, you take a negative 1 step by x, and then 2 of them up by y. So when we actually write this out, the notation, by the way, is you take that same nabla from the gradient, but then you put the vector down here. So this is the directional derivative in the direction of v. And there's a whole bunch.
Okay, let's write that down. Okay, there are a lot of different notations, it seems. But let's finish the video, then we can add that
Of
stuff.
other notations too. I think there's like derivative of f with respect to that vector is one way people will think about it. Some people will just write like partial with a little subscript vector. There's a whole bunch of different notations, but this is the one I like. You think that nabla with a little f down there with a little v for your vector of f, and it's still a function of x and y. And the reason I like this is it's indicative of how you end up calculating it, which I'll talk about at the end of the video. And for this particular example, a good guess that you might have is to say, well, we take a negative step in the x direction, so you think of it as whatever the change that's caused by such a step in the x direction, you do the negative of that. And then it's 2 steps in the y direction, so whatever the change caused by a tiny step in the y direction, let's just take 2 of those. 2 times partial f.
Okay, good. So this makes sense then. Actually, yeah, that makes a lot of sense. So in the direction, you multiply the gradient, you multiply the vector. Well, no, I don't think you're multiplying the vectors there, but you're corresponding the coefficient um in the directional vector. So in like v, you're corresponding the coefficients to of h over there to the coefficients over here of the partial. So partial x, partial y.
Partial y. And this is actually how you calculate it. And if I was going to be more general, let's say we've got a vector w. I'm going to keep it abstract and just call it a and b as its components, rather than the specific number.
Oh, wait. So how are you getting that again? How are you? Wait, I'm not too sure about this. How are you getting v? Like, how did they do that? I'm not too sure about how they did. I'll rewind and watch later, but wait, so x squared and y v. So if f of x comma y equals x squared y, then the partial derivative will be that. Fine. How do you find the direction of that though? Like, how do you find that v is equal to negative 1/2? Negative 1 and then 2.
Numbers, you would say that the directional derivative in the direction of w, whatever that is, of f, is equal to...
It'll be a partial f
is the
partial x.
derivative of f with respect to x plus b times
Partial
the partial
derivative
derivative
of
of f
y.
with respect to y.
Okay, 1 second. I'll be back. No. Okay. Yeah, we're back. I have to go like pretty soon now, so let's just continue from here.
And this is it. This is the formula that you would use for the directional derivative. And again, the way that you're thinking about this is you're really saying, you take a little nudge that's A in the x direction and B in the y direction. So
Oh, okay. They're not calculating the directional derivative. Like, there's not. Sorry, they're not calculating the direction. They're just saying that you're given the direction and then you have to solve it. Okay, that makes more sense now. So let's do that then. H3, so directional derivatives. Find a direction. So find a direction and represent it as a vector. Well, actually, this is more of a process. So I'll just like write it as a list then. Find a direction and represent it as a vector. Let's say, and then let's say that v is equal to a comma b. Let's say that's your direction, right? So then you'll say, and vectors are bolded, right? So let's just do that then. Vector a equals ab. To continue now, then the directional derivative is the directional derivative is the um is a times df dx, or partial f partial x, I guess. The directional derivative, and then you do plus b times that. So you're adding them up now to give. Wait, you are adding them, right? Or are you? Yeah, yeah, you're just adding them. So you're actually evaluating something. Plus b times partial f partial y. The directional derivative is this. Now what else is there? The notation to use is okay. Wait, this is not limited to just two direction. This is not limited to just two um dimensions or inputs. And then when the notation some like some different notations are. And what are these different notations? Well, let's just Google that and see. Notations. He mentioned a few, but I'll have to copy paste anyway. So let's just do this then. Uh, okay, there's that directional derivative. Let's see. I'm sure they'll have it here in Wikipedia. They have obviously they have everything there. So you can write it as this. Oh, and actually, there's also a limit definition there. I don't think it matters though. Okay, this is the directional derivative. So let's just leave it at that then. Okay, calculus. For wait, maybe they have a section about it, right? Normal derivative definition properties. Okay, we'll get to all this other stuff later. Then right? It doesn't matter right now. Oh god, they're like tensors and stuff. And not that I know what any of that stuff is, but I'm just saying that doesn't sound easy. How do you copy paste this now? Is that not possible? Okay, that's yeah, I think you can copy paste it. No, you can't, can you? No, you can't. Wait, let's try in case un, in case this can be like in case this is supported. Yeah, it isn't. So we'll just like take a screenshot then. Okay, let's not get sidetracked. Basically, the formula is like this, right? Directional derivative of a scalar function. This is kind of all it is, right? Like you don't need anything else. This is the notation basically, right? This is what they said, and obviously you can include f of x, y, and stuff. Okay, wait. Sorry. screenshot this. And yeah, you can extend it in as many dimensions as need be. There's only one notation we'll be using, so we'll keep this then. I don't want this to like caption. Here, you can have, this is one notation, so okay. This is one notation for the directional with the direction or vector v. There can be multiple dimensions. Obviously, there can be multiple dimensions or inputs. So you'll just change the x accordingly. Okay, that seems fine. There's very little information that we've got so far, to be honest. Like, just for example, this is something I was doing for chemistry. So there's like way more over there, and I didn't even take too long to do that stuff. So like maybe a few hours, like 2 or 3 hours. And here we've done already like what, 1.5 hours. And we don't have too much information, so we'll see.
So this should kind of make sense. And sometimes you see this written not with respect to the partial derivatives themselves and the actual components A and B, but with respect to the gradient. And this is because it makes it much more compact, more general if you're dealing with other dimensions. So I'll just write it over here.
Wait, this is the cross product. I'm pretty sure because you multiply the terms, right? This is the cross product. Oh, sorry. I meant dot product. It was just a slip. I meant dot product of the vector and the gradient.
This expression,
Okay,
it looks
great.
like a
Let's
dot
write that down.
product. If you take the dot product of the vectors AB and the one that has the partial derivatives in it. So what's lined up with A is the partial derivative with respect to x, partial f, partial x, and what's lined up with B is the partial derivative with respect to y. And you look at this and you say, hey, AB, I mean, that's just the original vector, right? That's W. That's the vector W. And then you're dotting this with, well, partial derivative with respect to x in one component, the other partial derivative in the other component. That's just the gradient. That is the gradient of f. And here, it's nabla without that little w at the bottom. And this is why we use this notation, because it's so suggestive of the way that you ultimately calculate it. So this is really what you'll see in a textbook or see as the compact way of writing it. And you can see how this is more flexible for dimensions. So if we were talking about something that has like a 5-dimensional input and the vector, the direction you move, has 5 different components, this is flexible. When you expand it, the gradient would have
Yeah,
5
okay.
components.
This makes a lot more sense. I actually remember reading this too. Let me get that multiplication dot copy paste. I'm sure that it's somewhere here. Let's just plop that in there. The dot product right there. So that's the good way to write it, the neat way to write it. So this is the same as the dot product this. Yeah, and actually that makes sense, right? Because now there's no need to have this extends to as many dimensions or inputs as you need. So that's exactly what he said here as well. So that's good.
Vector itself would have 5 components. So this is the directional derivative and how you calculate it. And the way you interpret, you're thinking of moving along that vector by a tiny nudge, by a tiny, little value multiplied by that vector, and saying, how does that change the output, and what's the ratio of the resulting change? And in the next video, I'll clarify that with the formal definition of the directional derivative itself.
Okay, let's not do that actually. I think this is enough. Like we've done most of this unit here, right? We've done like the 4 videos at 3 videos after we've done 2 of the exercises. So we're like well over halfway done with this. We did the partial derivative stuff as well. I think this is like a good place to end it. And just to, keep everything nice and neat, I want to underline these big units here. And then let's see. Oh wait, you can put equations in this. Wait, then we should change this. Yeah, we should definitely change this. So how do you do an actual equation then? Okay, it does. It's what's that? I guess this is like latex then. So let it be. That's other stuff to figure out. I'm not really going to try to do all that. That's a lot. But let's leave it here for now. Then we figure out what directional derivatives are. Let me download this, and I will actually link this as a PDF or something. So let's export it. What all can we do? We can do a PDF or HTML. Let's do HTML first and see. Include subpages, include content, everything, include databases. We don't have anything. So let's export it then. And let's take a look here. Okay, so it's here now. Um, it went okay. Yeah, I'll just do it as a PDF. That seems easiest. But this actually looks like very nice and neat. Actually, this isn't bad. I'll do it as a PDF. That should have everything in it, hopefully. I'll make it like 70% because it's a lot otherwise. Export. Okay, so that took some time. I'll just do this and open it up. This should have everything in it, I believe. Oh, I accidentally opened it in Microsoft Edge, so just ignore that. Yeah, I'll send the link in the chat. Well, actually, I'm not uh, going to send the link. I kind of forgot how to do that. It's a stupid thing, but I forgot. So, like, I can download it and then I'm sure there's some way to send that from Google Drive, but no one really needs it anyway, I think. This is there wasn't much right now, so let's ignore that. Meanwhile, we've gone for like over 1.5 hours now, so that's way too much, I think. I'll end it now. Uh, so I'll end it now. Thanks for watching. I know this was like pretty rambling. It might not have been very interesting, but this is also my first time trying to figure out how to do something like this. I think I'll have more interesting stuff to do in the future.